All right, so let's keep going. Remember, we're working on shaft design, and basically we're trying to see these different. I mean, if you have gears connected to each other, what's going to happen? So here this will be direction. Forces. Mating. Spur gears. Okay, so remember here, this is not complicated to understand. Again, let's say you have here one gear connected to a shaft, and here you have another one connected over here. What's going to happen over here to the forces? So basically what's happening over here. So I can look at this problem, let's say by doing this type of figure here. All right, let's say it will be gear A, gear B. And I think the other day we already mentioned that if this one is going clockwise, this one is going to go what? Counterclockwise, okay? And here we have, let's say, the component of the tangential will be the force. And this will be the rated component of the force. Okay, so that's basically what it is. So here, the only thing I just want to notice is that, so forces between A and B can be determined using, let's say, the summation of moments equal to 0. Action reaction principle. So, for example, if you have WT in this direction for gear A, what will be the action on gear B? You will have what? Same force, but on the opposite direction, no? Action, reaction. Yeah? All right? This is just, I know you know that stuff, so it's just pretty basic. All right, so I'm going to skip this. I'm going to skip this. Okay. I'm skipping a bunch of stuff. I used to cover all this stuff in Machine Design 1, but they told me that right now it's more covered in detail into Advanced Machine Design. So I'm not going to cover as much detail in material, in detail. But basically, we can have, if you want, a 30 seconds discussion, okay? Let's say you have a motorcycle, okay? You see that some motorcycles can use maybe for transmission. Generally, is what, three types of transmission. The more traditional one will be what, to use a chain, no? Some of them may use a belt, no? A rubber. And some of them, I think, like the BMW, can use like a direct shaft, no? All right. But let's talk about the first two, okay? So, or discuss the first three. So, what is the difference that you see between a chain, a metal chain, and the rubber chain, the V-belt?
Stretch it.
The stretch of it. So which one do you think will be able to transfer more power?
Is it like a CBT kind of thing?
No, not transfers. I'm talking about like drive belts on a motorcycle.
Yeah, on a motorcycle, or bicycle. Instead of having a chain, let's say you have like a pedal. Okay, so generally the advantage of the chain is that it will be able to transfer more power because we have less information. Okay, but also the other thing is that with some of these metal, if you have any disagreements, it might break more easily. The good thing of having some V-belt or something that rubber is that if you don't have a perfect misalignments, it's more forgiving. That's why I think you see more in custom bikes that of V-belts, no? All right, because you need a perfect alignment because chains are not good in strength laterally, no? All right. Obviously, then what is so that was between these two? The one that is direct, I think it's called carbon, the one of the BMWs. Okay, that one probably can transfer a lot of power, but something maybe it can be what the maintenance or the weight. No, it's going to weigh a lot more than a belt or a chain. Okay, but just want to say there's different stuff that can happen. Right. So something that I'm just going to cover is that in order to accommodate, I think we've seen that before, is that in order to accommodate, let's say, a gear on a shaft, you need to do something that is called, you need to create a key on the shaft where to install the gear. Okay. And I think I asked you if you were seeing this kind of stuff in what, ME304 or something like that, which is a lab, and you told me that no. Okay. But basically, so what happens if you're going to make a cut on the shaft in order to be able to install the gear? Because you make a cut, this is going to create some type of higher stresses around that location. No? Okay, so how do you take into account high concentration of stresses is what we're doing next. So this is on the old time, this is done by using stress concentration factors. I think this is the type of stuff you should see in 208. 205, what is it? 205 or 208? 208, okay. So for example, first one, would be the shoulder. Yeah, so that one is basically, let's say that you have two shafts, and let's say that here of different diameter. So let's say you have here D1. And D2. And all this stuff is common sense, it's not rocket science, okay? I know you know this stuff, but for example, if you look at that, what is better to do? To have a sharp edge or to try to round it off? Round it off, no? And what is the reason? It's because you might have some stress concentration in those areas, no? Okay. So one, this is fillet, sharp. Okay, so this is experimental data, but if you have a sharp side, you can have a stress concentration factor called KT equal to 2.5. And if you have a fillet here, the stress concentration factor is 1.5. So if you want K of T is stress concentration factor. Obviously, this is not, I mean, this is, remember that when all this stuff was done, final element were not really that available, no? So basically, you agree that this 1.5 is probably going to depend a lot on what you do here on the fillet, because we're not in Katia or Solboard, you can just decide what is the radius, no? So you can do more or less. All right. So that's the kind of stuff I think you should do in that class. to know how to create. And not for these ones, but I could create one. All this stuff already. If you do good fine element programs, you should see what is the value in stress in that location without having to apply this now. But just remember, in the old times, if you don't have fine elements, so what did you do? You just assume the structure to be rectangular, okay, sharp edge, and then at the end you will apply the stress concentration factors, okay, for your design. All right. So this is one. I think the next one probably will be for look at the. Okay, I don't have it here, but. Maybe we can look at it very quick. I'm surprised I don't have it here. Okay. I mean, let's talk first the one that's about the gears, and then we do the other one. Okay, so let me put it here. The next one we're going to look is at the E6. Okay, so again, like I said before, if you have here your shaft and you want to attach your gear, generally it will be attached here into a key, okay? Where you can see the gear. So once again, there's different ways to create a key. So one way is called the phi key, and this one is mill. So this is different manufacturing techniques if you want. So in this one, let's say you have here your shaft. Okay, you take the milling machine. And you make some type of groove, no? All right, so if you want to look at this from the side, this would look like what? Like probably something like this. Then if you want, you can decide to sharp or to round off this edge, okay, will look something like this. Okay, you can have a key at the top and the bottom, but let's say here I just do it at the top, okay, for simplicity. This will look something like this, no? Okay, and this will have to do with the milling machine. Another one will be another option will be, let's say that because of the tooling, you don't have that much tooling accessible, so you decide here to just make a cut. So you can put your gear. So in that case, if you look at it from the top, you probably look like this. Then it will be something like this and something like this. But just do one edge. This is what you will have. Okay, this one is called a sled runner. Sorry for that. Forgot to put it sled runner. This one you can just do it with a cutter, okay, with a circular saw or something. You can just go to the end and cut it, no? All right. So you see, this is two different options, and the two different options will depend on what is the equipment that you have available in your machine shop. Okay. So let's say the profile. So in this case, this will give you a stress concentration factor of 2.0. And this one here, the sledge runner, will give you a stress concentration factor of 1.6. So you see, all this stuff depends on different manufacturing techniques, though. Yeah, different options to attach the gear. It depends on manufacturing technique. Okay, the other option would be to use a retaining groove. So in this case, if you want, you could just create a groove all around. Retaining groove, yes. And this one, you could create that, or what's the name of that machine? With a lathe machine, now you could create this one easily. Okay, let's say lathe machine. You just put it there as it's turning, and you can create some type of groove, no? And then you can attach it to this. In this case, the stress concentration factor is considered to be 3. Okay, for this is not important, but since I have a video about it, maybe I can ask you to do it. This is not for the gears, but let's say here, in a plate, we have to go look for the value, but let's say you have this, and this, and for this, there is rules, even when you do the CAD's problems. So let me just Google it. Like, you see, I use Google. Don't think I don't use it. So, stress concentration factor for a hole. I think it's square root of 3 or something. Okay, you see, you have tables over here, but hopefully I find out an image. Okay, they tell you the diameter, they have the equation. I mean, they have different curves. You see here for the sled runner. Okay, this is good. It's good that I came here. Okay, so for the sled runner, you see here, depending on the radius of the fillet, you can have different curves for different values. We can go to design books and you can find these ones. All right, you can find it over here. Then for holes, if you want, it's kind of the same, but let's just look at this one here. This is the more traditional one. All right, here we go. So you see, it goes from a factor of 3, from a factor of 3, stress ratio is 3. And if you do find an element, you can actually find out that is actually around 3, the value. I thought it was square root of 3 or something. And no, but that's good. So you see here the same thing. Now if you do a hole on a shaft over here, let's say, you see the stress concentration factor KT will depend on the diameter, and there's rules that the hole cannot be closer than to the wall, no? All right, Jali, you want to leave, as a rule, you want to leave at least 1 to minimum 1.5, I would say, the diameter before getting to the edge, no? If you start making holes, okay? So you see that you have a bunch of tables in order to do this stuff. Here you have another one to create 2 holes. You might have here another one for the fillet, for the torque, for all kind of stuff. But to tell you the truth, I think all that stuff is a little bit outdated, because now that you have access to finite element, they should give you the correct stress right away, no? If you do a good modeling. All right. And that is something that actually you start doing in advanced machine design, or even we could have done in this class if we all had computers. I could have shown you how to create basic models for finite element for shafts. All right. All right. So after doing this, so let's over here, we say the stress concentration factor K of T is as well 3.0. Okay. And don't mix this one, I'll give you all this stuff. Yeah, I think this two today. That's it, too new. All right, so. I'm going to change the order here of the nodes. Okay, so we're going to look at dynamic criteria. So you remember that we look at the static oil criteria that were what? We look at the maximum and minimum principal stress. We look at the maximum shear, and we kind of talk about it. I didn't give you any problem, but it's really the most widely used for isotropic materials is the von Mises, no? Okay. If you go to a finite element program, generally you will ask to get the results. You can either get the von Mises, you can either get the principal stresses or the maximum shears if you go to the menu of a finite element. Right? Okay. But what is the difference of a shaft? Is that a shaft is moving. If it's moving, it is dynamic. No? Okay. So we cannot use either one of these criteria. So what do we need to use? All right. So the most widely used one, it has different names because it has, different a lot of people use there's little variation, so it's multiple names for these ones. But the main name is called Goodman. Criteria. So first, we're going to look at what is the possibility of loadings that we have. All right, so let's say you have a shaft over here. Let's say that is only rotating, okay? And let's say that for this shaft, oops, 1, 2, 3, 4, I'm gonna need. So since this is dynamic, we need to look at it in function of time. And let's say that this shaft, is just rotating. Okay, let's say it's just rotating. Okay, and it's given if you want transmitting a power. But we can, if you look at the stress basically is just what is called fluctuating. Okay, and this one we say that since this one will be the same value over here, let's say it will be sigma max. This will be here minus maximum stress. Okay, will be the minimum. So in this case, since you go to one side to the other side and you have the same value, this one is called, so case 1. Fully reversed. Okay, then here we're gonna have case 2. We'll see how we call it now. But basically in the case 2, we kind of do something similar. But this time, we still have our shaft, which obviously will be rotating. But let's say this time, for any reason, there is one force being applied over there, okay? A constant force, let's say it's a weight. Okay, so then what's gonna happen? That force over here is going to create a static stress. All right, so let's say you remove, if you don't have the shaft moving, or you only have this force, what's going to happen? What's going to happen to this? It's going to create a stress just due to F, no? And now, if this is moving, again, it's fluctuating, then what's going to happen? It's going to create a fully reverse stress, but about this one over here, no? So if I do 2 over here, if I go 2 over here, then over here will go 2 again, 2 on top, 2 at the bottom, but it will not be about the 0 line. It will be about this stress over here that will be due to the static load, to the static force. Does that make sense? Okay. Basically, in this case, this is 0, since there's no external force, and here we have another one. So in this case, you see sigma max, sigma maximum is not the same as the minimum because you will have sigma m, and this one is called fluctuating. All right, so let's see. Over here, the sigma sub m, so the stress sigma sub m is called mid-range stress. Now I'm going to plot some stuff over here. Sigma sub A, which I'm going to plot now, is called the alternate stress. And the alternate stress will be the distance, maybe in blue, is that distance over here. That would be the alternate stress. And you can find that the mid-range stress can be found as doing sigma max plus sigma min divided by 2, and that the alternate stress can be found by just doing the difference, sigma max minus sigma min divided by 2. Okay, does that make sense? Yeah? All right, see? Okay. So let's see, I change the page, I'm gonna write, so for the reverse, fluctuating cases, women cannot the following criteria. So I do the figure and then I explain how you come up with this, and you will see it's not, I mean, use common sense. All right, so in this case, you're gonna have here the mid-range stress, and here on the Y you have the alternate stress. Okay, so leave this figure in blank, and then I explain how so let's say how to construct or draw the Goodman. Let's over here line, okay? This is just to explain. So what did he do first? First he says what? If shaft not rotating, so basically it's just due to a static load. So if it's not rotating, what does that mean? Is that this stress over here is not going to exist, no? Yes. So we can say that the alternate stress in that case will be equal to 0. So in other words, we have static loading or static loading. So if you want to look at it, let me do figures. I like to do figures. All right. This is the stress. This is the time. So okay, so this is the figure that I did before. If you want, it's just one force being applied, okay? In that case, what do we say? The stress will be constant, and here will be equal to the sigma sum mid-range, no? Due just to the static force. Okay, so in that case, again, if it's static, let me just do another figure. So if the loading is static, what does that mean? We already talked about this. What is the name of this curve? Yeah, the stress strain curve, which basically is stress equal to E epsilon, where this is the stress. What's the name of this equation? Okay, perfect. Hooke's law. And we discussed that this curve is obtained experimentally by using the ASTM machine, no? Okay, well, you stretch it, I don't stretch it. So basically, let's say if you look here at the stresses, we say you can find or here you can use the yield stress over here, that will be the end of the linear part, or you could use, let's say, the ultimate. Okay, so here that's what is different cases, all right? So basically, if the alternate, if you go now to this figure, sorry. So now if we go back to this figure, so we know the alternate is 0. Right? And now from this figure, you can either use the yield value or you can use the ultimate value, no? For your design criteria based on this. So if I have this point over here, let's say I use the ultimate. So this is 0 over here. I can just say that the ultimate here, let's say my criteria will be this one here, the ultimate. Or if you want, I can use here the yield value, no? Does that make sense or not? All right.
In most design criteria, you use yield, right? Unless it's like a
Yes, I mean, depends on the what happens is that depending on the design, you will have different design criteria, you know, based on experience. But yes, if you want to be safe, I will use the yield, and you can use then a larger safety factor, or you can go to the ultimate and use a lower safety factor. The other way around, you can use to the ultimate and use a larger safety factor. You go to the yield and use a lower safety factor. Okay, that's the decision of the engineer. That's the stuff that you need to be trained at, and your design will depend on your personal judgment. Okay. All right, so now, obviously, this is the first case. It will be like if it was static over here. What do you think is going to be here, the second case? If shaft is rotating, so basically dynamic, but in this case, what you're going to have, we're not going to add any external force. So what is that going to mean? That the mid-range stress will be equal to 0. Okay, so basically now we are here at 0, and basically now we're trying to find is that what should be the value here for the maximum alternate stress. Okay, now this is a different story because now this is moving, no? Okay, so okay, I'll go to the next page because of what you know I said. I'll write it maybe over here. So using, I mean, I give you the name, but it's not important. The Palgram minor criteria, maybe I define it later on. Okay, this is what is called SN curves or fatigue curves. So basically, S stands for stress. Anyone guess?
Number of cycles.
Number of cycles. You are more accurate. Number of cycles. So again, this is, sorry, I need to go to the next page, but basically the Palgram minor, so SN curve so if you look here, if you do the curve of S and curve, which is a stress, these curves, I mean, in real life, they look like this. Sorry for that. Sorry. Yeah, I took it out before. These curves look like that. Yeah, in real life, they look like that, okay? I'm not going to give too much. So obviously, what happened? If the stress is high, let's say your shaft is going to last not a lot of cycles, no? But as the stress is lower, any time is going to last more cycles. Yeah. Okay. So basically over here, you can decide to. So let's say this will be the S value. Or here you could have sigma sub E. I guess sigma sub E will be the endurance stress. Okay, and again, this is number of cycles. Okay, so let's over here. obviously, the SN curve is obtained experimentally. That's not that difficult. You just take generally you take one coupon element of material, you attach it to a shaker now, and for a certain frequency, you make it go multiple cycles now, and you observe when it's going to start failing. All right. So sometimes you can observe when it's going to start, the yield property are going to start changing, or you can take it all the way to the when your coupon or your element of material is completely destroyed after the cycle. Does that make sense or not? Okay, you have different ideas. So in some cases, let's say you can say your endurance could be, let's say, based on yield. So let's say once the material start losing the properties, or you could say that this one will be based on the, let's say, on the ultimate. Okay, so if I go back to my initial page, all right, so that means that we have here 2 points, and here let's say we could base our equation here, let's say on the yield, or let's say on another one that will be the endurance. So what happens is that there is multiple lines, okay? But the original one, the Goodman line is the one that goes from the endurance one to the ultimate. So you need to make a straight line. C is the original Goodman line. Okay, so some people can use, for example, they want to go from the endurance to the yield. It will be going down. But the other ones that we're going to study is the modified Goodman line is the one that goes from this one to the yield, if you want. This one here should not overgo to the other side. Okay, so this is modified Goodman line, and you can have different options. So, and from the figure, you can see which one is more restrictive or not. So, for example, what do you need to have? So you can calculate what is the stresses, the ultimate, your yield, or the alternate. You can find what is your mid-range. You can find what is your alternate, and what happens. So let's say we just use the Goodman line. Okay, so forget about this one. So if the values, if you are in this area over here, so let's say the Goodman line. So for the Goodman line, what do we say? We move from here to, it's not to the endurance, sorry, to the endurance, to the ultimate. So what's going to happen over here is that if you're in this area, what's going to happen? Is your structure safe or not, or is it going to break? In this case, will be safe, and here will be not safe, no? So basically you can see here. So which one do you think is more conservative over here? Let's say you need to choose your design between the Goodman line or the modified Goodman line. Which one do you think is more restrictive? The modified will give you less space, no? I mean, I don't know, it will give you less space at the beginning, but will give you more at the end. And the one will be the reverse, no? So you see, it can depend more or less on the design. And again, you have some lines that go actually from this one to the ultimate. That would probably be the most conservative, no? And whoever decided to use that one, they give it a different name. It's like modified Goodman line, and they put a name of somebody else. Okay? Yes.
You want to copy like 5 minutes for class?
Yes, but I was to give the copies.
Oh, okay.
Which I just did. But thank you anyway. Okay. Man, we're not going to do a lot more today. So Does that make sense? How did I come up with the idea? It's not rocket science. You just say, I'm first gonna come up with this point by assuming the load is static. So I know it's gonna fail it's gonna break due to failure. And then on the y direction, say, okay, now I don't apply any static load. I use the Pargram-Minor equation to find out what will be the endurance, no? Stress. He creates the points over here and just connect those 2 points on a straight line. Does it make sense that in a straight line? I have no idea, but he uses the simplest assumption is that it's a straight line, no? It might be an ellipse, it might be quadratic, I have no idea. Okay, but that is what it is over here. So let's stop over here for today. And now, as you can imagine, as we work with the shaft can be subjected to combined loading, as you have on the exam, and at the same time to be rotating, no? So to be subjected to an alternated stress. And now you need to determine what is the life of that shaft having combined loading and rotating. Okay? If I don't put a code 5, remind me, okay?
My exam, this one.
Okay, we got 4 things now.